Okay, Assalamualaikum and very good morning. So again, this is Microwave Engineering, SEET 3573 for Section 1. Okay, so these are the syllabus for this course. You can read through the details from the course information file. So for last week, we have discussed on brief introduction to microwave engineering, and you have had 4 group presentation on some applications of microwave engineering. So this week I'll cover on the waveguide structures and some of the microwave parameters. So, and next week we are about to continue with transmission line theory and also impedance matching. So what is a waveguide? Okay, so last time I have mentioned that when we have a communication system, you have the transmitter, transmitting antenna, and we have a transmitter system which consists of the coupler, the filter, and etc. And the signal will be transmitted via a medium, either it is a free space or a guided structure, and the guided structure is called a waveguide. So then the signal received by the receiver, okay, and received by the end recipient. Alright, so in the receiver there's also microwave circuit involved, again such as coupler, filter, and etc. So by definition, a waveguide is a structure that guides wave, okay, such as electromagnetic waves or sound, with minimal loss. Since it is a guided structure, so the signal will be traveling. For example, this is the structure. So we have the input, the signals. Okay, so the signal will be traveling into the structure. So this is a waveguide. So usually it travels inside the structure by a reflection between the walls inside the structure and then receive at the end. Okay, so then it produces quite efficient transmission with minimal loss of energy by restricting the transmission from one end to another end. Okay, so basically it is a hollow metallic tube, so it could be in a rectangular shape or a circular shaped structure, okay, depending on the overall structure of the system. Okay, so for transmitting electromagnetic waves by successive reflection, okay, as I've shown here, so there's reflection between the inner walls inside the structure. So from the transmitting point to the end point, so at the end the signal will be passes through to the end recipient or the receiver system. So what are the main characteristics of a waveguide? So it is basically a tube. Okay, this is a tube, whether it's in rectangular or in circular shape or in any other shapes, and it provides distributed inductance, while the empty space, so the empty space is hollow structure, so it's empty space between the tube walls provide distributed capacitance. Okay, and the structures are bulky, heavy, and it's expensive. Okay, however, it's very efficient if compared to other transmission medium, especially the free space. Right, and the advantages of waveguides: easy to manufacture, can handle very large power in kilowatts, power loss is very negligible or it's very minimal, and offer very low loss, low value of alpha attenuation, And the microwave energy when travels through waveguide experience lower losses, okay, or related to losses if compared to other medium, for example, coaxial cable or free space medium. Okay, so these are some examples of microwave structures that handles microwave frequency signals. So the following are the example of the waveguide. Example: rectangular, coaxial, circular, microstrip line, horn, and cavity. Right? The which structure or which waveguide suitable for which application you need to determine the application first and look at the allowable space or the consumed space where the system will be placed or will be applied. Therefore, you can decide which waveguide structure is the best for your system. Okay, let's look at the rectangular waveguide. So rectangular waveguide is a rectangular metal pipe, or is basically a rectangular hollow metal tube with dimension A multiplied by B. So A is the width and B is the height of the structure, which guides high frequency electromagnetic waves from one place to another without significant loss in intensity or in efficiency. Alright, so the signals traverse along the waveguide, so from one end to the other end, okay, by reflecting or by reflection in between the inner walls of the structure. So okay, along the waveguide, so it can travels in a number of modes. For example, TE10, TE11, TM10, TM01, and so on. Okay, so for example, the basic or the dominant mode for rectangular waveguide is TE10. So it's basically TE means that the transverse electric. Okay, it's transverse electric. Okay, in which the electric field is basically in transverse if compared to the direction of propagation, right? So in this case, the direction of propagation here, for example, so the electric field is transverse or in perpendicular to the propagation direction or the structure, the broadside of the structure. Okay, so if we look at how the signal travels inside the structure, so from the top view, we can see that the signals basically moving in circular motion, or basically representing and the number of circles, okay, depending on the mode. Okay, TE10, one represent only one half wavelength signals is seen along the structure. Okay, one half wavelength. Okay, this is the structure. Okay, A and B. So TE10 meaning that it is a dominant mode where the electric field is transverse to the broadside of the structure. So this is the broadside of the structure. So we can see only one half wavelength. Okay, half wavelength of signal travels along the structure. Okay, if you cut, okay, this is how the signal travels along the waveguide structure. So when you see it from here, okay, you can see only one peak at this point. So this basically representing the dominant mode TE10, and it's usually at the lowest cut-off frequency. Okay, so what happens when you have other mode, high modes, TE20, for example? TE20, TE20, meaning that you have two half wavelength signal across the broadside of the structure. Okay, so in here you have two half wavelength. So this is representing the TE20 mode. Okay, so you'll see these two, there'll be two signals, a wave, or we can see the E-field pattern across the structure when you look from the top view. And when you have other modes, for example TE30, 3E11, so one, and if you have one here, it's basically another signal from the shorter side of the structure. Okay, or here you can call M and N. So M is the broad side of the structure and N is the shorter side of the structure. Okay, this is the equation of the cutoff frequency and the wavelength at the cutoff frequency for rectangular waveguide. So the FC in Hertz, okay, if you use omega, then you need to consider 2 pi. So it's basically 1/2 epsilon naught mu naught. So permittivity and permeability of the structure, of free space permittivity and permeability multiplied by this equation. So M is the number of half wavelength along the broad side of dimension of the structure. Okay, the broad side. So how many half wavelength? Okay, if only one, then M equal to 1. For example, TE10, so the M equal to 1 and N equal to 0. Okay, so the lambda C, the wavelength of the signal at the cutoff frequency, can be calculated by this equation. So meanwhile, at the lower cutoff frequency or dominant mode TE10, in which the M equal to 1 and N equal to 0, so the cutoff frequency for the waveguide can be calculated by this simplified equation. So E is basically the broadside dimension, or the width of the waveguide, rectangular waveguide structure. Okay, these are how the fields looks like inside the structure from top view and also from the side view. Okay, these are from the top view. Okay, depending on the modes the signal being transmitted. So in this case, we can see, if you look at this point, only one peak in the middle, so it is basically TE10, and here you can see two peaks, so it's TE20 and TE01. Now in the broad side is 0, but you have one at the shorter side here. Okay, so TE01. Okay, so E field is when it's in TE mode, is when the electric field is perpendicular to the broad side, and for H field you measure the magnetic field across the structure, so it's perpendicular to the broad side of the structure, and on the other side is when you cut it or you view it from the front view, okay, or the side view. Okay, this is an example of a practical or commercially available waveguide structure, so in which it is R100, so it's dimension 22.9 multiplied by 10.2. So alright, so the A and B as given, and when the structure is measured, so it can cover the frequency of operation between 8.2 to 12.4 gigahertz. Okay, so and the cutoff frequency is 6.5 to 13.114. Okay, so the cutoff frequency is usually measured at -3 dB from the maximum point, I believe that you have seen this kind of signal from your board plot or in the signal and system syllabus, right? So in which at -3 dB point, the power at this point has been reduced by at least 50% from the maximum. Okay, here is P, the maximum power transmitted. So at -3 dB, the power has been reduced by at least 50%. Okay, so the bandwidth of the signals can be calculated by the size or by the difference between the maximum of the cutoff frequency to the minimum cutoff frequency measured at -3 dB point. Okay, next is the magnitude of transmission, the calculation of magnitude of transmission in dB. So as usual, the magnitude of transmission or the power transmission is usually expressed in decibels. So the magnitude can be calculated by either using the power or the voltage ratio. Alright, so if you are using the power ratio, so you should remember that you need to use 10 log 10 of P output over input. Or if you use the voltage ratio, so you need to make sure that you use 20 log of 10 V output, the voltage output, divided by the input voltage. Alright, so let's look at an example. As I have mentioned earlier, that when you have 50% power loss, it is actually represented by -3 dB lines from the plot, okay, from the power plot, and it is actually equivalent to 70.7% or 70% of voltage loss, which equivalent to -3 dB point. Right, so let's check this value. For example, you have P max equal to 1000 watt. Okay, so 50% reduction is actually 500 watt. Okay, let's look at the dB values, right? So for when you have your P max equal to 1000, so at P max 1000, so it is actually equal to 30 dB, 10 log of 1000, and at -3 dB or 50%, it is actually equal to 27 dB. Okay, if you compare the maximum to the 50% one, okay, so 30 dB minus 27 dB, so you get 3 dB reduction of the maximum power if compared to the one at -3 dB. So you can see that there's 3 dB attenuation or reduction in power. Okay, so same goes to the voltage. Okay, you can revise again your signal system calculation when you have the power loss and also voltage loss. Okay, the tables basically summarizes some of the magnitude transmission in linear and also in logarithmic. Right, so you can try to check this out, just a basic conversion. Okay, the following tables show the commercially available waveguide structure and its frequency of operation, the cutoff frequency, minimum and maximum, and also its dimension. So it covers various frequency bands, L band, S band, C band, X band, and so on. Okay, so these are some of the applications of rectangular waveguide. So we can see the construction of the rectangular waveguide. You have the metal tube, okay, being constructed where it's being cut, Okay, and each of these elements will basically controls how the signal travels. Okay, it will affect the efficiency of the transmission. So later we will look at this design, and you can simulate, okay, how the input signal being transmitted through the waveguide structure. Okay, this slide shows another examples of rectangular waveguide application. So usually when it is constructed as an array, multiple element in one structure, and it's usually used for radar tracking and radar cross-section. So this one example shows that where the rectangular waveguide is implemented or applied on a cruise. Okay, so it's basically provide the positioning, okay, radar tracking and global positioning during a trip or during a journey. And sometimes it is used in military mission as well. Okay, next we are about to look at the coaxial waveguide structure. So I believe that you are familiar enough with coaxial waveguide. So it's basically the coaxial cable that consists of inner and outer conductors with radius A and B, and you have the outer jacket, outer conductor dielectric that separated the outer conductor to the inner conductor. Okay, and the dielectric having its permittivity, and the characteristic impedance of the coaxial waveguide can be calculated by using this equation. So B and A are the dimension of the inner and outer conductor. Okay, and the permittivity epsilon naught, the free space permittivity, and the dielectric permittivity, and also the free space permeability is as shown. Okay, for if the dielectric material or the separator between the outer conductor and the inner conductor is air, so the the permittivity is equivalent to 1. So if you use Teflon or polyethylene foam, or the foam is having the permittivity of 2.06 and 1.25. So basically the epsilon C is depending on the dielectric materials you use inside the coaxial cable itself. Okay, and in general the medium between the conductors is filled with air or the low loss dielectric materials. Okay, usually the Teflon. Okay, the figures show the commercially available coaxial waveguide or coaxial cable. Okay, and mostly the RF cable or coaxial waveguide use standard coaxial line with characteristic impedance of 50 ohm. So what's basically characteristic impedance? What is Z0? So Z0 is basically the ratio between the current, the ratio between the voltage to current for a wave that travels along the transmission line. Okay, so it's basically the resistance it will exhibit if it travels in infinite length. Okay, so the standard Z0 or the characteristic impedance is 50 ohm. Okay, usually when you design a cables or the RF structure or RF transmitter or receiver, so it's usually matched to 50 ohm. Alright, so and it depends on the dimension. For example, here is B over A, and for air, if you use the dielectric as air or Teflon, it will give different ratio of impedance. Okay, this table summarizes some of the commercially available coaxial line or coaxial cables or coaxial waveguide. so in which it has a specific dimension B and A, and the ratio and also the cutoff frequency of each structure. And for coaxial waveguide, its fundamental TM mode, its fundamental mode is TEM mode, and the second mode resonant is called TE11 mode. Okay, for rectangular waveguide, the fundamental mode is TE10, but for coaxial waveguides, it is TE11 mode. Okay, so TE11 mode can be propagated from the so-called cutoff frequency, and the cutoff frequency for coaxial waveguide is given by C over lambda C, the wavelength at the cutoff frequency, which depending on the B and A of your coaxial cables or coaxial waveguide. So C is basically the speed of light. Okay, this slide shows the cross-sectional visualization of the field distribution in fundamental TEM mode of coaxial waveguide and higher order or the second mode of TE11 mode. Okay, for coaxial waveguide. So in TEM mode, it's transverse electric and magnetic. So you can see that the E field is basically transverse, okay, or perpendicular to the cross section of the structure, the both side of the structure. So it's perpendicular. Okay, and the H field also is perpendicular to the E field. Okay, for TE11 mode, if you remember in coaxial waveguide, when you have TE10, okay, TE101, you have one half wavelength across the broadside. But when you have TE11, meaning that you have one half wavelength on the broadside and one on the shorter side. Okay, so one on the broadside here, and you have another one on the shorter side. Okay, so that's why when you look at the B, figure B, that's cross section. Okay, there's a crossing between the E and also the H field. This is the manufacturer's operating frequency for 50 ohm match air field coaxial line. So the dielectric here, or the separator between the conductor, inner and outer conductor, is the air. Okay. And next is the circular waveguide. It's basically more or less the same as the coaxial waveguide, but circular waveguide is basically a circular hollow tube. Okay, but for coaxial cable or coaxial waveguide, it has two inner conductor and outer conductor separated by dielectric. Okay, for circular waveguide, so as mentioned, it is basically hollow circular structure with radius R, okay, or hollow metal tube. Okay, and it support both the transverse TE and TM modes, transverse electric and transverse magnetic modes, and its dominant mode is TE11. If for coaxial cable or coaxial waveguide, the dominant mode is TEM mode, and its second mode is TE11. But for circular waveguide, its dominant mode is TE11 mode. Okay, the signal at TE11 mode propagates with minimum degradation or minimum losses. And the circular waveguide is basically easier to manufacture if compared to rectangular waveguide, and it's relatively easy to install. And real application is usually being used to connect a horn antenna with a reflector, and example of application is in radar tracking and also for long distance transmission above 10 GHz frequency bands. And to calculate the cutoff frequency of circular waveguide, okay, we can use this equation: Fc equal to 1.8412 multiplied with the velocity of light or speed of light divided by 2 pi r. R is the radius of the circular waveguide structure. So we can see that basically the cutoff frequency of the circular waveguide is inversely proportional to its radius. Okay, and finally, the slide shows different mode of circular waveguide transmission, so in which you can see that different distribution of the field intensity depending on the mode of transmission by using circular waveguide. Okay, basically we have ended the first part of the waveguide structures, so I'll continue with other different types of waveguide structure in the next part 2.